our last little mini lecture, we talked about displacement. We go from here, we go to there. Now we want to talk about velocity. It's related to the change in displacement, the rate of change of displacement. So in other words, you displace this much, and then later you displace that much. Okay, so the amount of displacement per time. So this is really the rate of change of displacement. Okay, we start off defining average velocity. Average velocity is simply the displacement over time. And so that means that you start here, okay, and you walk over here, okay, and let's say you walk 12 feet and you take 3 seconds to do that. Okay, so the average velocity, we sometimes write average velocity V with a bar on the top, or V sub average as your book does. That's going to be, in this case, 12 feet over 3 seconds. So that would be 4 feet per second. Remember from our discussion in chapter 1, distance per time is unit of velocity. Okay, so this is our average velocity. And now once again, you know, we can think about it as something that has sign. Okay, so we've got our origin right here, and we start here, we end here. So, you know, if this is x naught and that's my final x, then that means that the displacement is positive, so it's greater than 0. Okay, since the average velocity is delta t over delta t, or delta x over delta t, that means that this is also greater than 0. Okay, we always go forward in time. We don't go backwards in time. And so delta t is going to be always positive. And so that means that positive displacement means positive velocity. You know, likewise, if we started here x naught and we ended there at x, okay, so in that case we went this way. Now delta x is less than 0, therefore the average velocity is also going to be less than 0. So it would also be negative. And so velocity has sign. Again, if I had put my origin here, like that, and if that was x naught and that was x, now in that case we have velocity that is positive. Now once again, the direction that you pick, when you pick an origin, you pick which direction is positive, and so that defines the direction, that defines the sign of the displacement, which therefore defines the sign of the velocity. Well, average velocity is a very coarse sort of concept, because as I said, we might have someone walking here and they walk a certain distance here and it takes a certain time to do that, okay, but they might have gone part way, you know, slowly, then sped up. So the problem here is that we want to know the velocity at some instantaneous moment. So in other words, as this person is going from here over to there, I want to know right there what's their velocity at that point. So here, so you measure velocity as delta x over delta t, so displacement. So we have some displacement. Velocity, you have to have a displacement. You don't get a velocity if you're not moving, if you're not changing anything. And so there's a displacement over a certain amount of time. And so what we want to do is have that time interval get very, very small. So we want to take a limit as the delta t between the x naught and the x final right here. As that time gets between those two spots gets very, very tiny, okay, then we want to know that's going to give me my velocity right in the middle, the instantaneous velocity. And so all we have to do is compute that. Well, if you remember, one way of writing delta x is x at some t plus delta t, okay, minus some x at t. So we want to take the limit of, as t goes to 0, of x of t plus delta t minus x of t, okay, divided by delta t. Well, gosh, you recognize that. You know what that is. That's a derivative. So now we know that the velocity is the derivative of displacement. So if I have a function, if I say that x equals, 4 t plus 5, so 4 meters per second t plus 5 meters. Okay, and so that means at x0, at t equals 0, so if the time is 0, if time is 0, then x is going to be 5 meters. At 2 seconds, okay, then x is going to be equal to 13 meters. Okay. Well, I want to know what is the velocity. Okay. So to find the velocity, I could say, well, I changed 8 meters in 2 seconds. Okay. Or I could say the velocity is dx dt. And so if I take the derivative of that, I get 4 meters per second. Derivative of 5 meters, it's a constant, so that's 0. So this gives me the velocity right there. All right, so now we have an expression for figuring out velocity. Okay, now at this point, it doesn't matter when I did the derivative, it's a constant. Okay, but it's possible you could have had a more complicated equation. So x could have been 1.5 meter per second squared t squared minus 1.0 meters per second t. Okay, and I want to know what's the velocity. So velocity, v dx dt, when I take the derivative, I get 3.0 meter per second squared times t minus 1 meters per second. Well, that's a function. So that means at t equals 0, that's when we start. The starting point, if I plug that in, the velocity is minus 1 meters per second. So that means it's moving to the left or moving in the negative direction 1 meters per second. But after 1 second, if I plug that in, then the velocity is 2 meters per second. So 3 meter per second squared, 3 meter per second squared times 1 second is 3 meters per second minus 1 meter per second. And so that gives me an answer of 2 meters per second. So that's the velocity at time 1 second. If I wanted to find the velocity at 10 seconds, I would do the same thing. I'd take the derivative, I'd plug 10 in for t. And so now we have an expression for figuring out the velocity as a function of time. What you do is you find the equation of position, the position equation. Okay, so it says x equals. So this is your equation that tells you where is the object. And then you take a derivative of that equation, dx dt. Okay, and then that is going to be an expression or an equation that describes your velocity. Okay, so